With the rapid escalation in the size of wind turbine generators, WTGs, the transportation and installation processes for offshore wind farms are encountering unprecedented logistical challenges, which complicates the efforts to increase offshore energy production. The current capacity of installed turbines hovers around 9 megawatts, with an anticipated rise to 11 megawatts within the next year. And projections indicate that the latest turbine models, showcased by leading manufacturers, could reach capacities of 15 megawatts within the next 5 years. This significant upscaling brings formidable engineering and logistical hurdles, primarily due to the vast dimensions of individual components. For example, turbine blades are now approaching lengths of 130 meters. While they are relatively lightweight, their sheer size presents substantial challenges for secure storage on a ship's deck. Transporting these blades transversely on deck introduces the risk of blade tips contacting the water due to the vessel's rolling motion. Longitudinal transport, on the other hand, is often constrained by the vessel's length. Moreover, the upcoming generation of nacelles is projected to weigh as much as 1,000 tons and require hoisting to heights up to 150 meters above sea level. This represents a dramatic increase from the capacities of current vessels, many of which were originally designed for 3 megawatt turbines, which weighed around 150 tons and required lifts to only 80 meters. This rapid evolution, occurring in less than 5 years, a fraction of the typical vessel lifespan, has necessitated frequent, costly upgrades to ensure ships can continue supporting the latest installation demands of wind farms. Building massive offshore wind turbines requires unique processes, as these structures are designed to withstand harsh marine environments, rather than being placed on land or mountainous areas. Ensuring durability against seawater corrosion and structural strength is crucial. Here's an inside look into the precision-driven steps used to construct these engineering marvels on the Machinery and Technology channel. Step 1. Optimized plate cutting. The process begins with the precise pre-cutting of steel plates used to form the turbine's cone-shaped tower sections. Each plate is carefully shaped to minimize material waste, with each cut strategically planned to reduce the need for additional adjustments. This method not only conserves resources, but also allows the cones to be rolled in one swift motion, enhancing efficiency. Step 2. Preparing plates for welding. After the plates for the cones and cylindrical segments, or cans, are cut, they undergo edge milling. This preparation along the shortest sides ensures smooth, strong welds when the plates are assembled. The exact milling also aligns edges perfectly, minimizing the risk of misalignment during the welding process. Step 3. Efficient assembly lines with dual-side welding. In the main assembly area, 3 identical production lines handle the welding of plates from both top and bottom without flipping. This setup enhances safety and reduces handling time by eliminating unnecessary repositioning. Once welded, the plates undergo precise milling to refine the seams, ensuring a seamless finish and structural integrity. Step 4. Quality control and process adjustments. To maintain the highest standards, each weld is immediately inspected for accuracy. Any irregularities are flagged, allowing operators to make rapid adjustments and avoid delays. By closely monitoring weld quality in real time, the process minimizes downtime for panel repairs and maintains a continuous logistical flow within the production hall. Step 5. Forming the cans and cones. The welded plates are then rolled into their final cylindrical or cone shapes. Thanks to advanced machinery, each cone can now be rolled automatically in a single motion, from flat metal plate to precise, curved sections. This innovation not only speeds up production, but also enhances safety by reducing manual handling. Step 6. Final welding, grinding, and calibration. After rolling, the sections are welded, ground, and calibrated to achieve exact alignment. Cranes, largely dedicated to this stage, facilitate swift assembly by positioning heavy sections efficiently. This dedicated lifting capability keeps production moving smoothly, reducing time gaps and maximizing productivity. The combination of precision-cut plates, automated rolling, dual-sided welding, and real-time quality monitoring defines the modern construction of these offshore wind turbine towers. Each step is crafted to ensure resilience against the ocean's corrosive forces and to streamline production for rapid deployment of these colossal renewable energy sources. Offshore wind turbines, situated in oceans and large lakes, must be constructed from materials specifically modified and optimized for the challenging marine environment. Unlike land-based turbines, offshore wind structures endure constant exposure to salt water, which necessitates enhanced corrosion resistance and mechanical resilience against unique loading forces. The partial submersion of offshore towers introduces not only corrosion challenges, but also new dynamic loads due to water movement and wind shear. Higher wind speeds, a key advantage of offshore locations, create additional loading stresses, especially from the differential shear between the upper and lower turbine sections due to variations in wind speeds across the tower height. Furthermore, offshore towers encounter significant buffeting loads as waves impact the base, leading to the prevalent use of steel tubular towers engineered for these demanding conditions. To protect against the corrosive effects of seawater, particularly at the splash zone, where waves break against the base of the tower, the steel used for monopiles and turbine towers must be carefully treated. Two primary anti-corrosion strategies are often employed: cathodic protection and advanced coatings. Cathodic protection involves attaching sacrificial anodes, typically made of galvanized metal, to the monopile. These anodes possess a higher electrochemical potential than the steel, drawing corrosion away from the primary structure. Additionally, coatings play a critical role in mitigating corrosion-induced damage, including pitting, which can lead to hydrogen-induced stress cracking. Common protective coatings for offshore wind structures include hot-dip zinc treatments and multi-layer epoxy systems finished with a durable polyurethane topcoat. These approaches collectively enhance the structural longevity and operational reliability of offshore wind turbines in harsh marine environments. Specialized jackup rigs, known as wind turbine installation vessels, WTIVs, are essential for installing both foundations and turbines in offshore wind projects. As of 2019, next-generation WTIVs are under construction with enhanced capabilities, including the ability to lift loads between 3,000 and 5,000 tons to heights of up to 160 meters. These advancements support the efficient handling of increasingly large and complex components. To improve installation precision, advanced gyroscope systems stabilize heavy loads during installation. Furthermore, Dynamic positioning technology allows the vessel to maintain exact stability and orientation, especially when operating the vibrating pile driver essential for foundation installation. Monopile foundations, widely used for their economic efficiency in shallow water offshore wind farms, have become the primary choice for fixed bottom installations. Each monopile consists of a single, large diameter structural element designed to bear the entire load of the above-surface wind turbine structure. Constructing a monopile foundation typically involves driving a massive hollow steel pile with a diameter of up to 4 meters and wall thickness of about 50 millimeters, approximately 25 meters into the seabed. The process includes penetrating a 0.5 meter layer of larger stone and gravel, which reduces the risk of erosion around the pile. Once the pile is deeply embedded, a transition piece, pre-fitted with necessary features such as boat landing structures, cathodic protection, cable ducts for subsea cables, and a flange for the turbine tower, is attached. The hollow center of the pile is then cleared of sand and water and filled with concrete to secure stability. Finally, an additional layer of larger stones, with diameters up to 0.5 meters, is placed around the seabed surface, providing long-term erosion protection and structural durability. This advanced monopile construction method enables robust and lasting support for offshore wind turbines in dynamic marine environments. To facilitate the installation and stability of offshore wind turbine towers, these structures are constructed in two segments: the underwater section and the above water section. The two segments are joined by a specially designed transition piece, secured with a grouted connection that effectively transfers the loads experienced by the turbine to the stable monopile foundation below. To enhance the strength and durability of the grout, weld beads known as shear keys are incorporated along its length, helping to prevent slippage between the monopile and the tower under heavy loads. Given the massive size of offshore wind turbine components, minimizing transport between manufacturing and assembly sites is crucial. As a result, dedicated offshore wind port facilities have been strategically developed in regions with high concentrations of offshore wind projects. These ports serve as critical supply chain hubs for large-scale offshore wind farms, streamlining assembly, storage, and deployment processes for turbines and infrastructure. For electrical transmission, high-voltage alternating current, HVAC, is typically used for shorter cable routes under 80 kilometers, as it is more economical and simpler to install. However, for distances beyond 80 kilometers, high-voltage direct current, HVDC, transmission becomes the preferred choice due to its superior efficiency over long distances. Unlike HVAC, HVDC systems minimize power losses by reducing reactive power transmission, allowing efficient energy transfer over extended routes. HVDC is thus ideal for offshore wind farms located far from the shore. The installation of submarine power cables presents significant technical challenges due to the harsh marine environment, including high waves, strong currents, varying water pressure, and seabed obstacles. This complexity requires advanced technology and specialized techniques beyond those used for land-based cable installation. HVDC transmission cables offer several advantages over HVAC cables. HVDC systems are unaffected by charging currents and incur significantly less power loss, making them particularly suited for long-distance undersea power transmission. However, HVDC cables require power converters to integrate with the AC grid onshore. While line commutated converters, LCCs, are a mature and cost-effective technology, voltage source converters, VSCs, provide enhanced control over both active and reactive power, offering greater flexibility in grid management for offshore installations. This balance between efficiency, cost, and control makes HVDC technology a promising solution for transmitting renewable energy from offshore sites to the grid. To transport energy from offshore wind turbines to onshore power grids, extensive cabling must be laid along the ocean floor. This cabling is crucial for transferring high currents efficiently, requiring both advanced materials and strategic placement to optimize performance and reduce material use. Effective cable designs must address durability and conductivity challenges, often balancing cost against efficiency and resilience to oceanic conditions. A primary cost-saving approach involves substituting traditional copper conductors with lighter aluminum conductors. However, aluminum's lower density compared to copper poses a risk. Aluminum cables may experience greater motion from underwater currents, increasing the chance of abrasion or damage. Engineering solutions are therefore needed to stabilize these aluminum-based cables, as failure could disrupt the energy supply and increase maintenance costs. Installing these cables is a costly endeavor, with materials and deployment costs reaching up to $400 per foot. Considering the vast lengths of cabling required, spanning hundreds of thousands of miles across the global seafloor, this represents a significant financial investment by both public and private sectors. What are your thoughts on these engineering challenges? Share your ideas in the comments below. Your insights could help drive the development of more resilient and cost-effective solutions for this essential infrastructure.